Hi, I'm Adolph Oliver, and this is a video clip explaining how functions work. Now, functions actually are kind of a shorthand, so we're not going to be doing anything we haven't done before here. So, to begin with, first thing we'll say about a function is it tells how one variable relates to another. Now, what we've been doing in the past here is saying, well, given x, what's y? So we're talking about how x relates to y. But other letters can also be used, s relating to t and so forth. Now, let's look at some ways that we can indicate that relations exist, and then we'll point out here what's special about a function. One of the things we've done is we've indicated xy pairs as ordered pairs like this. So here's a set with 4 different xy pairs indicated. We can also have ordered pairs indicated by, well, it's in effect, we make a graph here. So for a given x value here, if we come down and hit the graph line and come across and hit y, this x here then relates to this y, and different graph lines will give different relations. Now, here's another one. It's maybe a little bit new, but often is used, talking about clouds. And you write down the possible x domain variables here in the first cloud, let's say 2, 3, and 4. And then the y range values that are possible, let's say 7, 8, or 9. And the arrows indicate this 3 here will go to 7, this 3 will also go to 9, this 4 will go to 7, and so forth. Well, now, what we have to do is tighten up this relation idea a little bit, because functions here have an additional rule that has to be followed. So let's talk about this. A function has a special rule about the relation. Every time we have a certain x value, that always has to go to the same y value. So in other words, when you have an x come up, it better always go to the same y. What can't happen is we can't have that x go sometimes to one y value and other times to a different y value. It's always got to be the same to be a function. So let's take a look now at these examples we had up here and see who makes it and who doesn't. Now, back to the ordered pair up here. We have x equals 2 going to y equals negative 3. We have x equals 4 going to y equals negative 3. We got x equals 2 going to 5 and x equals 4 going to negative 3. Well, the x 2's show up in more than one place and the x 4's do. But notice the 4 here, every time it shows up, it goes to negative 3. So it's always going to the same y value, but we've got a problem with the 2's here. This x equals 2, this time goes to y equals negative 3, and this x equals 2 here goes to y equals 5. Well, because these guys are going to different y values, this is not a function. Okay? It fails simply on account of the given x value 2 sometimes goes to negative 3 and sometimes goes to 5. And that can't happen. Every time the 2 shows up, it would have to go to the same value. So this 2 going to negative 3, if this one here also had 2 going to negative 3, it would be a function. Now, graphs. We've worked a lot of these. X and y, and we got our graph line here. So if you pick a particular x value, come down, hit the graph line, come across and hit where the y value is on the y-axis, then you see that this x right here is always going to go to this y. So there's no way to goof this up when you have a nice linear graph line like this. So this is a function. Let's look at the cloud business here. Okay, the x values here, the domain values, are in the first cloud. The y values, the range values, in the second. we indicate how things relate to each other by drawing arrows here. Remember, domain always gives you the range. So we have here 3 as an x value going to 7, but we also have 3 as an x value going to 9. Well, since this 3 goes to 2 different y values, and we don't know whether it's going to go to 7 or 9, then this is not a function. It is okay if there are other x's that go to that same y, as long as every time 4 shows up it goes to 7. But remember, when you're talking about xy values, they all have to follow the function rule to be a function. And as long as there's just one of the relations that goofs up, okay, where the x value goes to different y's, and we see that here in the cloud, so it's not a function. We saw that up here in the ordered pairs, so it's not a function. But this graphed example would always be okay because every x is always going to go to the same y. Wherever we find x values here, it'll be the same y it goes to. Okay, well, that's an introduction to the idea of requirements on a function. Now, let's talk about how we actually make use of these guys. And so here comes the useful stuff on this. Function notation, why do we use it? Well, it's actually just a shorthand to write down what we want done with a minimum of words. In fact, really no words at all. And one of the important things as you go along in math, you'll be dealing with things that are more and more complicated. It's nice not to get tangled up in a ton of words, so that's why they invented this function notation. Let's show you how it works. Okay. Now, what this function notation indicates is something we've already done. It's really just substitution. Okay, so let's give you an example here. Instead of saying these words, substitute the value x equals 2 into the equation y equals 4x minus 3, we can just indicate the following. F of 2 equals this guy, f of negative 1 equals this guy. Well, how do we come up with these? Here's the point down here at the lower end of this. Let's take a look at it and then we'll come back and talk about these guys. What we do in the original equation, remember we had it up here, y equals, we replace the y with f of x. So I take this original equation and write it f of x equals 4x minus 3. Everything on the right side stays the same. All we're doing is replacing the y with f of x. Now, if what we see in the parents behind the x here happens to be the variable, then we just leave the variable in the equation. Now, by the way, you have to realize now, in the old days here, you'd think that f next to something in parents meant multiply. But notice the difference here. We're saying f of x equals, and we're giving the equation over here that it equals. So now you know this is not multiplication. F is a common letter that they use because it stands for, function. But you can use G and H and any other letter you want here to set it up. But you define what the equation is using your function notation. F of x equals 4x minus 3, and you can have over here whatever you happen to be dealing with. If the variable is still in the parents in the x, then that means the variable stays in the equation. But let's go back up to these guys. Okay, if you have f of 2, then that means this x down here is being replaced with 2. So you look at the rest of the equation here and say, okay, I'm going to replace this x with 2. These are multiplying, so it'll be 4 times 2, and then there's the minus 3. So we got 4 times 2 is 8, minus 3, I think that's 5. So f of 2 would equal 5. Now what if we have a different value for x? How about f of negative 1? Now we did the same thing. Go down, replace the variable with the value we want, negative 1. So we have 4 times negative 1 minus 3. Now let's see, that's going to be negative 4 and minus 3 more. I think it's going to be negative 7. So here it is. Once you've been told what the equation is, okay, it's been defined like this, then all you have to do is say f of 2 or f of -1 or f of whatever value you want, substitute it in, and you can figure out what the value is. You can do these guys without saying any words. So remember again, this is the idea behind this. What we're able to do here is shortcut all the language in this and be able to indicate much more concisely what we want. Okay, let's look at some examples here. Here we're using the letter G to stand for our function. It's as good as F, no problem. So the original equation, g of x, which means we'll have the x value in the equation, here it is, equals -2x plus 5. And what we want to find is g of 8. Well, okay, what's g of 8 going to equal? Well, we simply do this. We're going to replace the x with 8. So -2 times, remember the 2 next to the x means we're multiplying. I put the 8 in here, plus 5. So what do we got here? Well, let's see. -2 times 8, I think, is -16. And then plus the 5, I think it's -11. So we'd say g of 8 equals -11. Well, what you substitute in here doesn't have to be a whole number. It could be a fraction, a decimal, any old thing. So here's another one. W of x equals x minus 7/4. Find W of -5/3. Okay, well, that means we're going to replace the x with the value given right here. So in the equation, you see the x. Well, I'm going to replace that with -5/3. Here it is. Okay, let's make sure I got that correct. -5/3. Okay, minus 7/4. Okay, well, this is a simple basic math problem. And we got two fractions we're combining here. We need to have a common denominator between 3 and 4. I think it's 12, huh? So I got to multiply top and bottom of this equation by 4. So if I do that, I'm going to have -20 over 12. Now let's double check this. If I reduce this, 4 would go into 12 3 times, 4 would go into 20 5 times, and I got the minus. So always double check that you got these guys right. Now the second guy over here, I got to multiply top and bottom by 3. So -21, 3 times 4 is 12. Now if I double check this, okay, 3 goes into 12 4 times, 3 goes into 21 7. So I look good. Well, these are both negative. Okay, we of course have got our common denominator 12. So -20 minus 21 is what? -41, I think. Okay, and I don't think there's anything in 12 that will reduce into 41. So if the answer is negative, the thing we normally do is put the single minus sign out in front. Here it is, -41 over 12. Okay, here are a couple more examples. P of x equals 0.3x minus 1.7, and it says find P of -2.3. Well, it's this -2.3 that we want to substitute into the x. So I can say, okay, P of -2.3 is going to equal, well, I've got 0.3 here times the x, which is -2.3, and then we're subtracting, looks like -1.7. Well, okay, we're back in basic math here again. Remember, this is 0.3. Let me get that decimal point there. So this is going to be negative. We got one negative sign. 3 times 3 is 9. 3 times 2 is 6. Okay, and we need to have 1, 2 decimal places, so this is going to be -0.69. And of course, then we have negative 1.7. Okay, well, they're both negative. There it is. So if we combine these together, let's see, we'll have the 9 on the end. 7 and 6 is 13, carry the 1. So it looks like negative 2.39. Okay, would be what the value is. Now, see what we're just doing substitution here. And the function notation just allows us to indicate what needs to be done without using all kinds of words. Okay, now, here's the other thing that can happen. You can substitute anything in here. It doesn't have to be a number. And so here's another example where we've got g of a equals negative 2a plus 3. But we want to find g of negative 3z. Okay, well, g of negative 3z. Now, what that means, of course, is what we're going to be doing is substituting this negative 3z in for the a. So it works just like you do it with numbers, only you got letters here. So negative 2 times the a value here, which we're plugging in negative 3z, and then we have plus 3. Okay, so let's clean this up. Negative 2 times negative 3 is going to give me positive. I'll put a plus to rub it in here. Plus 6, and we had the single z here. Okay, and then we have plus 3 on the end. Okay, well, there it is. We can't combine any further because this term here has a z in it, and this one doesn't have any variables, so we're stopped right at this point, but there it is. G of negative 3z equals 6z plus 3. Okay, here's the last couple of examples, just showing again what we can substitute in. Notice the original equation, g of n here, equals, what do we got? Negative 3n plus 1. And what we want to do is find g of n squared. Well, that means we're going to take this n squared and replace it with the plain n. It can be the same variable like this. There's no problem with it. So what I'm going to do is say now g of n squared, okay, because that's what we want to do, equals negative 3. Now we're replacing the original n with n squared. All right, there it is, and then we're adding 1 to it. So here we go. Clean it up. We got negative 3n squared plus 1, and that's as far as we can go with this one. But we found g of n squared by replacing the original n with n squared. Now, of course, what you substitute in doesn't have to be a single term. It can be a binomial or higher like this. And so in this last example, what we're saying here is we've got, let's see, g of t, and we want to find g of t plus 4. So what we're going to do is take this t plus 4 and replace it wherever we saw the initial t in the equation. So I'm going to have g of t plus 4, here we go, okay, equals, and let's see what we got here, negative 2 times t squared. Now, remember now, the t is being squared. We're replacing the t with t plus 4, but since the t was squared, we got to square this. There it is. And then we have after that the minus 2. Okay, let's do some cleaning up here. Now hopefully you remember how to take a binomial squared, the shortcut we have. Okay, this is a perfect square trinomial. We'll come back and get to minus 2 in a moment here. First we want to multiply this out. So we square the first guy. We got t squared. We square the last guy. Plus 4 times plus 4 is plus 16. Okay, then we make the one rainbow we can. This is our shortcut that we learned for this. Plus 4t, multiply together the values in both ends of the rainbow here. But then, hopefully you remember what you have to do is double this when you bring it down. And you just double a number. So it's going to be plus 8t. Now, that whole thing was being multiplied by negative 2, so we still got some work to do. And of course, we got the negative 2 in the end over here, so let's not forget that. Okay, now, better distribute in here this negative 2 to everybody inside. So here we go. Negative 2 times t squared, negative 2t squared. Negative 2 times plus 8, negative 16t. Negative 2 times plus 16, how about negative 32? And then of course we have this minus 2 in the end. Well, these are like terms here, so we got to combine these. So I end up saying down here, okay, g of t plus 4, okay, equals negative 2t squared minus 16t, and then negative 32 minus 2 more, negative 34. Okay, so there we are. Well, again, this function notation is a nice shorthand, and it's just substitution. Okay, and once you get the hang of this, it'll go real quick for you.